Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. Till now we had an exhaustive discussion on the vibration response of a simple single degree of freedom system, and we explored variety of different excitation to this vibratory system and understood how the dynamic behavior of this simple system is. It is imperative for us to now migrate to the complexities of a practical vibratory system, and an intermediate step to that is to study more than 1 degree of freedom system, and therefore, it is appropriate for us to get started with a 2 degree of freedom system and see what differences lie between the dynamics of the single degree and 2 degree of freedom systems. I would like to now take a recap of what we have done till now in terms of the contents of the course. We all started with a single degree of freedom system. We essentially tried to understand the importance and significance of vibration analysis, and then started with a simple model, and that is what in literature always called as the single degree of freedom model. And then we looked at different ways to model, ways to get governing equation of motion, finding out natural frequencies, free vibration response. So, response to initial conditions or initial excitation or initial perturbation was discussed for a simple model. We also then understood different types of damping that are possible in the practical situation. So, here we studied viscous damping model, the Coulomb or dry friction damping model, as well as the structural damping or material damping, also known as hysteretic damping. After that, we discussed Duhamel's integral or a convolution integral as to how that is used for finding out response to arbitrary excitation or so to say transient short duration excitation to the single degree of freedom system. And needless to say that the same approach can be extended to other complex vibratory systems. So, you would see later that whatever we learned for a single degree of freedom system as excitation in different ways will be applicable obviously to other higher degrees of freedom systems. Then we trained our attention on the response to external forcing function, which is more sustained in the sense that excitation function is not short duration and does not necessarily exist for a short duration of time. It is actually a sustained continuous external excitation, and that excitation is a function of time, as we know. So, in that we studied two different kinds of excitations: harmonic excitation, which is quite prevalent given the mechanical system being subjected to unbalanced excitation, because there are always rotating elements in the system. So, we extensively analyzed the response to different ways of harmonic excitation. The excitation could come from the force acting on the inertial mass, or the force could be through the base excitation or a base profile or a base motion. In either of these two cases, we explored how the response is obtained for a given excitation frequency. We also discussed what is transmissibility in the case of a harmonic excitation, and displacement and force transmissibility were discussed, and we also understood how the vibration sensor design is based on the fundamental principles of vibration response. Okay. Then we looked at how a periodic excitation, wherein the forcing function is not strictly a harmonic function of time, can be accounted for by making use of the linearity assumption and implementing or invoking the principle of superposition. So, the response to periodic excitation was investigated. So, these are all what we have learned till now. If you recall how the overall discussion in the course so far has gone in. Okay. All right. So, with this background, now we are all set for exploring further, and we will now try and see that in as it happens in many practical systems, that you may not really be able to capture all the dynamics by forcibly presuming that the system can be modeled like a single degree of freedom system. Like for example, in this case, if the wheel mass is significant and you model the chassis and the rider mass as a one rigid mass, and then the suspension springs, the two different suspension springs here, and then the wheel itself like individual independent mass, and then the stiffness of the tire will be modeled like another spring. So, then the system becomes a little more involved, and not only that, it is the degree of freedom. For example, if in the previous all discussions we assumed that the motion is only vertical motion, right. So, the degree of freedom assumed was only vertical linear motion. Okay. But as we all know that this chassis is a distributed mass, right. So, it has its own mass moment of inertia about the axis perpendicular to the plane. So, obviously, it will also have a tilt motion, right, that we never included in our analysis. So, all of that would throw up some interesting response features, and that is the reason why having discussed single degree of freedom to to all its finer details, let's look at how things change and what new things appear in the analysis modeling when we consider more than one degree of freedom. Okay. So, instead of jumping directly to multiple degrees of freedom, wherein we start taking many number of degrees of freedom, it makes sense to first understand by addition of an one more degree of freedom, what are the essential changes that we can expect, and learn from it little better. Things will be little manageable and easier to comprehend, and therefore, instead of migrating straight away from 1 degree to maybe 10 or 15 or 100 degrees of freedom, it makes sense to see how a 2 degree of freedom system's formulation is obtained, how the natural frequencies are obtained, and what do they actually make sense, and what are mode shapes. You might have all learnt earlier what is the meaning of a mode shape. So, we will discuss these aspects of a 2 degree of freedom system. All right, and then of course, we will later on get on with other things which are all lined up little later. So, when you talk of multi degree of freedom system, I mean more than 1 degree of freedom system, we always took the example of this vehicle, which is easier for us to relate to. So, we initially started with a single mass representing the chassis, and it is many times justified for initial level analysis, where the chassis mass is significantly larger as compared to the other elements which are isolated or connected with the spring. So, it makes sense to use a simplified model like this. So, this mass is actually that of the chassis and the rider combined, and the spring and a dashpot represents the suspensions. So, that looks okay. I mean what we then looked at the vertical motion as the only degree of freedom, as I mentioned to you, and that motion in practice is called as a bouncing motion. So, the degree of freedom which we prescribed here, maybe x of t or y of t, is a linear vertical motion, and based on that degree of freedom the governing equations of motion were derived. But as we discussed in the previous slide, what stops this mass or this system, the chassis, to have a tilt motion, or it can oscillate about the mass moment of inertia, about the center of mass. So, this kind of a motion is quite possible. Imagine you suddenly braking, during the cruising, you start suddenly braking your vehicle, you have all experienced the kind of pitch motion, okay, or a tilt motion of the entire chassis, apart from the vertical motion. So, this motion which is now shown here is called as the pitching motion, okay, and then you can have this system modeled with 2 degrees of freedom, maybe x of t as well as theta t, okay. You all have a basic understanding of what the degree of freedom mean for a given system, okay. So, this rigid mass will have, out of many other possible degrees of freedom, we know that in space it will have 6 degrees of freedom, but for a planar motion it suffices to consider x of t and theta of t. You may also include in the same planar motion another degree of freedom, okay. So, it can have a kind of a sway motion y of t, but generally this motion can be ignored to start with, okay. So, then we can have only 2 degrees of freedom. And as we mentioned, going further, if you want to consider the wheel mass, you can have front suspension, rear suspension, and then tire stiffness is all accounted for, and then you can imagine suddenly a simple system which we modeled earlier as a single degree of freedom system can turn into, well, you can have 2 degrees of freedom here the way we discussed, and we may ignore the pitch motion because the wheel, you cannot imagine the wheels pitching or having that kind of a motion. So, you can restrict the degree of freedom for the wheel to be only 1, and then it will become a 4 degree of freedom system, total of 4 degree of freedom system, and then you can individually look at the free body diagrams of each of these masses and then derive the governing equation of motion. Derivation of governing equation of motion is very straightforward the way we have discussed, and I shall discuss for a 2 degree of freedom system shortly. So, that you will have an idea, but that is how this whole system will get analyzed. Needless to say that if you have a simple single degree of freedom system like this without any other motion but the bouncing, we have now discussed threadbare as to how the resonance will look like. It will have a single resonance, right, because there is only one natural frequency. So, irrespective of what is your excitation frequency, if you scan through the entire operating speed range, you will encounter one resonance in this case, because 1 degree of freedom system, 1 natural frequency and 1 resonance. And this entire system will obviously have one governing equation of motion, okay. Okay, what happens when we have a 4 degree of freedom system? Because there would be correspondingly 4 natural frequencies, omega n 1, omega n 2, omega n 3, omega n 4, and then corresponding to each of these natural frequencies you can expect resonances occurring, okay. Some of them will be close to each other, some of them will be far apart, it all depends upon the properties of the system and the parameter values k t and m and so on. So, but the point is, when you have multiple degrees of freedom assumed in your model, you can expect such kind of a dynamic magnifier graph or a frequency response of the system, wherein you will have all possible resonances, okay. Of course, premature to discuss, but you may not see all of these resonances appearing in the response plot, okay. But the reason is that unless you have some kind of an excitation which can excite this rotational mode or pitching mode, you may not excite this, okay. If you only have this vertical excitation function, you may not be able to excite that kind of a pitch motion in the mass. Okay? Then you may not get a pitch natural frequency. So, it is not only necessary that your system should have that natural frequency, but your excitation function should be such that it should be able to excite that motion. Okay? But of course, that part we will discuss later as well. Okay. So, I will before I get into the details of the formulation part, let me give you a couple of examples here of how our 2 degree of freedom system would look like, or how it would be necessary to consider more than 1 degree of freedom. We have already discussed that in the context of that vehicle, but I think we have taken this example in the past, isn't it? We discussed a hoisting drum problem where this platform which houses a winch or a pulley system here, motorized pulley system here, operating a wire rope so as to lift a weight. Okay? And what we assume that the platform or a beam here has a stiffness Kb, and the wire being thin enough, small diameter, made of steel. So, it has some it has its own stiffness Kr, and the mass of the winch. Okay, so, let me write here as Mw. This mass of the winch is assumed small enough in the earlier analysis, and the weight here, so maybe ML is the load being lifted here. Okay. So, what we discussed in our earlier analysis is that this winch mass was negligible compared to the weight being lifted, and with that assumption, then what happened is that this spring which is representing the beam, and the spring that was representing the rope essentially is connected to only one mass here. Okay. And although they look orthogonal here, you can easily club them as a simple as a single spring, equivalent spring. In these springs being in series, you can finally get the entire system modeled like a simple single degree of freedom system. However, it all is going to be an approximation, because based on the the numeric values of the winch mass and the weight being lifted, one can approximate in the modeling process. We can ignore the mass of the winch, but suppose this mass being lifted is comparable. Okay. Comparable in the sense that if you are lifting a 1000 kg mass, and if this winch is 60 kgs, you can easily ignore the mass of the winch. But if this mass of the winch is, let us say, 200 kgs, yeah, you may still ignore it, but then the accuracy with which omega n gets calculated may be questionable. Okay. So, we need to figure out, and this is all by experience. We learn as to when to ignore, when not to ignore, and so on. If you do not want to ignore, then your analysis becomes little more involved. That is the catch, right. So, you cannot simply make quick calculation and get the response or the natural frequencies. So, more involved and more accurate your model, more time and more efforts are required to get the same output or the desired output. Okay. So, in here we are basically now going to assume that the winch mass or the pulley mass is it cannot be ignored, and then I will make a model which looks like this. I have a spring which represents that of the beam, then I have a mass of, let us say, pulley and or a winch, and then I have a spring representing the rope stiffness, and then I have a mass of the load or the weight being lifted or the stuff being lifted by the rope. And then I have one degree of freedom here may be x1 t as the degree of freedom with which this end of the beam is going to move, okay. And then I have an independent another degree of freedom with which the load, if perturbed, will move, okay. And because they are connected by this compliant element, they can be independently moving, right, they cannot be constrained to move together. You remember one case of tappet valve mechanism that we discussed, you remember that there was a spring here. This fulcrum was assumed rigid, and therefore, we could relate this motion with angle theta. You remember that to find out what is the strain energy stored, we had this written as x of t, and this motion was let us say y of t, sorry, x of t, okay. And I hope you all remember that this x of t was written in terms of theta, and this y of t was written in terms of again theta, in terms of these lengths maybe L1 and L2. This could be possible because this lever or a fulcrum, okay, in that mechanism was assumed rigid and it is not flexible, and therefore, theta and x and y, or x and y both were related to theta and they were not independent of theta. Here this mass can move independent of this mass because they are connected through a flexible element here. And so, you have a case here of a 2 degree of freedom system. Okay, we shall discuss by taking some representative numeric values of all these parameters to see how, in which case one can ignore and in which case one has to account for the additional mass. The other example is of a forging hammer. Now, many of you are aware how the forging hammer works. Essentially, the forging hammer is this part that a top or a hammer falls from some height, and this is the workpiece which is supposed to get formed. Okay. So, this is an anvil on which the workpiece is put, and the hammer falls on it, and then the forging take place, right. That is a very simple, straightforward. Now, to make sure that this hammer process or a forging process does not disturb the nearby places, you have one line of defense first here, that the hammer itself is isolated, okay. And it is usually for a good design, it is put on a concrete bed. So, this is a concrete bed on which the hammer is mounted, and so it is isolated through this pad of isolators. So, they are represented as springs, but they could be made of polymeric material and so on. So, a pad will isolate it, and then the concrete bed itself is isolated from the ground. So, this is basically your ground, right. So, based on the relative masses of the hammer and that of the concrete bed, you can model this either as a single degree of freedom system or 2 degree of freedom system, right. So, either assuming that the concrete bed is heavy enough and large enough, I can model this hammer to be a simple spring mass system like that. However, if the concrete bed is finite and it is its mass is not too high compared again to the mass of the hammer, then I will have to have the modeling revised and modified and updated to account for both the masses. Now, this is that of the bed and this is that of the hammer. So, this is the isolator stiffness here 1, and then this is the isolator at the foundation, right. So, this is how, I mean, it is all up to you what way you would like to model it, and and if you remember our basic vibration analysis process, did we not discuss that the first step is the most critical, most challenging step, right. There all your insights into your physical system, how best you know about your physical system, that plays a major role in the formulation or a modeling process. Rest of the process, the moment you get this, I mean once you have a few weeks of exposure and basic mechanics knowledge, you can simply get right up to the solution process. Then your mathematics comes into play and solving these equations. Again after you solve the equations, then again you have to go back and relate the response that you got, the output that you got, you relate back to this foundation, I mean back to this system. Okay. So, you need to then correlate what you are getting with your system. Let us represent this forging hammer, or for that matter any of similar systems that we have seen in the past. So, we now assume that some of the examples that we saw in the previous slides can be modeled like two individual masses like M1 and M2 here, and they are separated through these springs, maybe K1 and K2. Usually this K2 and K1 and K2 will suffice. For example, in the case of a hoisting drum, this is the stiffness of the beam, this is the stiffness of the rope. So, this spring may not be necessary, but just for the sake of completeness or illustration, we have included one more spring here. That does not make a big difference here in the analysis process. So, either K1 will be absent or K3 will be absent, and then the system will represents the original system. So, if you may assume that if you have a string which is fixed at both ends, then the total mass of the string can be distributed into two masses, and then the two masses will be separated by springs on the either side. So, this is a generic system. 2 degrees of freedom x1 and x2 are assumed here. You may assume for the time being that they are located at the mean equilibrium position. That means, the gravity now goes out of the picture, right. Whatever is the weight of M1 and M2, they are such and the stiffnesses K1, K2, K3 are such that somehow they will settle down at a equilibrium position, is not it. And this line which you are seeing here is the line representing their individual mean equilibrium position. Now, that helps us in understanding how x1 and x2 as a function of time would change. Okay. So, their motion will be relative to these two mean equilibrium position. Okay. The way we always used that mean equilibrium position for a single degree of freedom system, we never accounted for, or we did not need to account for the weight of the mass, and that weight of the mass takes care of the static deflection, and then this mean equilibrium position we find or define the motion with respect to this mean equilibrium position. So, on similar lines, these two masses are currently at their mean equilibrium position, and the responses x1 and x2 of these two masses M1 and M2 are relative to those two mean equilibrium position, very straightforward. Okay, now what is our process? You imagine that this is how we have initially modeled the system. Okay. Migrating from a simple model of 1 degree of freedom, we have now improved it or modified or updated it to a 2 degree of freedom model. Now, what is the next step? As we all have been going through that, the next step is to get the governing equation of motion, for which we need to get the free body diagrams made. So, let us look at the free body diagram of the first mass. So, I am now going to write it for mass M1. The motions are shown as they are, I mean the degrees of freedom are identified as x1 and x2. Without any loss of generality, I can assume that x1 is larger than x2. for the sake of getting all the forces recorded on this mass on the free body. Stripped from the surrounding, this body will have this connection element to the spring and this this connection point to the spring at the top and that one at the bottom. So, those are the only two connections of it with the surrounding, is not it? So, supposing that x 1 represents the motion going of the mass m 1 going down, how is the force coming from the spring k 1 will act? It will try to restore it and it will, the spring k 1 will be in tension. So, if this goes down, that means this mass is going to go down like this, there will be this much amount of stretch in the spring. So, the spring will try to regain its original unstretched position. So, the obvious direction in which the force will act from the spring k 1 is going to pull that mass back up, and we all know that an ideal spring will have its the restoring force generated will be proportional to the stretch in the spring. Now, one end being fixed here, the total stretch will be that of the motion at the other end, that is x 1. So, the restoring force here will be k 1 times x 1. Okay. X 1 implicitly is a function of time, that means x 1 is instantaneous motion of the mass x 1 and x 2 both. So, this force is an instantaneous value of that force acting upwards at the moment when the mass is going down, and k 1 x 1 is the value of that force, the magnitude the value of that force acting in the upward direction. Now, what happens to this particular connection point where the spring k 2 is connected? When the spring k 2 is connected to this mass, obviously there will be a force coming from the spring k 2, and that force is going to be what? Constant of proportionality is k 2, that is the spring rate, okay. And how much will be the stretch in the spring or the extension or compression in the spring? Now, make a note here that the springs have these two ends, that means the relative motion of the two ends is going to decide how much is the effective force acting. So, obviously, will it not be x 2 minus x 1 or x 1 minus x 2? It depends upon in which direction would you like to keep it like. So, with the assumption that x 1 is greater than x 2, that means this motion is higher than this motion, which means that the spring is going to be under compression. So, when the spring is under compression, it is going to restore its original unstretched position, that is going to push the mass upwards. Okay. So, this is going to be x 1 minus x 2 with the assumption that x 1 is greater than x 2. This can get released, I mean this is just an initial assumption. As the masses move and the dynamics change, x 1 and x 2 are anyway going to get calculated, and then accordingly it will flip its sign depending upon the instantaneous values of the difference between x 1 and x 2. Okay. Is that fine? Is that all? For applying the Newton's second law, what do you do? Mass times acceleration, summation of all the forces in the direction of acceleration. All the external forces that act on this free body, what are they? These are all the forces, right? And mind you, there the acceleration is downward here. So, in that direction, what are the forces acting on this mass in the direction of acceleration? Minus k 1 x 1, please make a note, this is acting upward, this is acting upward, and then minus k 2 into x 1 minus x 2. And then of course, you can get the governing equation of motion for the first mass m 1 x 1 double dot plus k 1 plus k 2 into x 1 minus k 2 into x 2 equal to 0. I clubbed the coefficients for x 1 while transferring all the elements from the right to the left side. On the right hand side you do not have any external force. Please remember that this system which you have shown here does not have any external force as of now acting on it, right. So, we are all talking about a free vibration case. There is no external excitation to the system. It will be all dynamics of this entire system once it is perturbed from its mean equilibrium position. So, it is a case of a free vibration analysis. Okay. Now, we have got the first equation for sure. Let us get for the second mass now, is not it, the way we did it for the first mass, the second mass m 2 will have similar acceleration downwards, and then when it tries to go down with the displacement x 2, this particular spring gets compressed because its other end is fixed and this end is being pushed down. So, from the mean equilibrium position it gets further stretched or compressed, and then the restoring force because of K 3 would be obviously K 3 into x 2, that is this being fixed, the other end being fixed. What about the other force coming from K 2? It will be simply equal and opposite to this force. So, I can represent this force coming from K 2 to be of the same magnitude, just that it is going to act downwards, mass m 1 pushes downwards with an amplitude greater than that x 2, x 1 is assumed greater than x 2. This spring is under is going to be under compression. So, that compressed spring will try to push the mass m 2 further down, and the force with which it will do is K 2 into x 1 minus x 2. You can otherwise consider the free body diagram of the spring itself, and then you will get the same force. Okay. Now, having done this, you can again simply apply the Newton's second law, and then I can write m 2 x 2 double dot equal to f x, which itself is now going to be the force now K 2 x 1 minus x 2 is in the direction of acceleration. So, that would be positive, whereas K 3 into x 2 is opposite to the acceleration, and I would write it as I have written here. Now, reorganizing this equation, m 2 x 2 double dot plus I can write this as K 2 plus K 3 into x 2, all right, and minus K 2 into x 1 equal to 0. That is my equation number 2. So, now because I have 2 degrees of freedom, I have 2 governing equations of motion. These governing equations of motion are second order ordinary differential equation, right, in x 1 and x 2. Now, the bigger question is step 3 is over. Okay. Step 1 was to get this simplified vibratory model from your actual physical system. The second one was to get the governing equation of motion from the third step was to get governing equation of motion from the simplified vibratory model. That is what we have done. The next step, the third step, fourth step would be to solve this, to generate response or to generate the dynamic characteristics to be obtained. Okay. So, how do you solve this? How do we solve this equation? We have got these equations, now they are required to be solved. How do we make assumed response now here, right? We need to make a valid assumed response in this case. Now, the equation is having two coordinates here, x1 and x2. I may assume a harmonic response, but that is like e to the power omega t, or I can also use the assumed solution as capital X cos omega t. So, the amplitude and the cosine function or a harmonic time function. Okay. I can use e to the power j omega t as well, there is absolutely no problem. What about x2? See, when they are independently moving, how do I ensure that the period with which this is going to move and the period with which this is going to move would always be the same, irrespective of how you excite them, and the overall system would be moving harmonically, the way we have assumed for a single degree of freedom system. So, based on the parameters of the system like M1, M2, K1, K2, K3, it is inappropriate to presume that the system is all going to move the way we saw in the single degree of freedom system, completing a perfect harmonic response, both of them at the same time. Okay. So, in general it is reasonable to assume that the response is not going to be harmonic, but will be periodic. Okay. And then you may have a response which is going to be periodic. If I push this mass and this mass together, same distance, okay, and for a hypothetical case that this stiffness is k, this stiffness is k, this stiffness is k, this mass is m and this mass is m, that means it is all, I mean their numeric values are such that all the springs are identical, all the masses are identical. Now, you start questioning what is the purpose of such a hypothetical case. We will talk about when this gets violated, what happens, but for the sake of some initial understanding, just imagine that both of these two masses are moved together with the same amplitude, okay, right, and then you release them. What is going to happen? Middle spring does not have any influence. Okay. Now, very nice observation. So, let us look at the equations themselves, and you will now realize the correlation between what equations are telling you and what the physical this movement is telling you. What does the equation tell you? That the governing equation dictates or decides how x1 is going to be, x of t. By solution of this equation you are going to get the response x of t, is not it? But that response is not only governed by your parameters like this, but the governing equation has a contribution coming from the other degree of freedom x 2. So, the equation is not independent, it is not independent only in x, it has a contribution or it has a term that is coming from the second mass x 2, which means that you cannot have independent x 1 motion happening. The moment there is x 1, there would be x 2, and whenever there is x 2, there will be x 1. Same thing is happening here. See this term of the equation, the two equations are coupled. So, they are not independent in x and x 1 and x 2. Okay. But here, and can we say that if somehow you make k 2 equal to 0, you can see, look at both these two equations, if somehow k 2 is 0, okay, the two equations become independent. So, when we are perturbing the two individual masses with the same amplitude and perfectly in sync, right, the motion of both of these masses will complete its periodic motion in the same period of time capital T. Okay. Now, if we perturb these two masses like this and then the ensuing motion would be with the same period, we can therefore, as a hypothetical case, assume the solution to be with the same frequency, both of these two masses with the same frequency, but they might be of different amplitudes. Now, here of course, we have assumed k and the k 1 and k 3 to be k, but if the stiffnesses are different, maybe this is k 1 and this is k 3, then perhaps the amplitude could be different. Okay. So, we are considering here a case where the two masses move with the same frequency, okay. And the interesting facet of this motion is that all the elements of the vibratory system will execute a harmonic motion. In this case, we have assumed only two. In general, they could be more of them. So, this motion is called as the principal motion. Where all the elements of the vibratory system, elements I mean M1, M2, would move harmonically with the same frequency and they would complete their one cycle of motion at the same time. So, they would start at the same time, end at the same time, and when that happens, you can imagine that they are perfectly harmonic, they are perfectly moving with the same period, and then the whole motion looks like a harmonic motion. This is something which is same as what natural motion that we saw for a single degree of freedom system. Now, there is definitely no doubt that the general motion is not going to be such a classy motion, okay. But at least let us look at a condition that would create this kind of a motion. I mean, in here for the sake of illustration, I tried to show you that okay, if we move them together like this and that makes this k 2 to be ineffective, then how the motion is going to look like, okay. But we would like to mathematically formulate a condition that would create this kind of a motion or generate this kind of a motion, and that is what the exercise that we are going to carry on. So, for doing that, we assume that the motion followed by both the masses or the solution of each of the masses is are given by this particular assumed solution, right. This is our assumed solution now. Now, if this is the assumed solution, we would put this assumed solution back into these equations, right. We would put these assumed solutions in the governing equation of motion and find out what we get. No? How will you do that? If you substitute these solutions in the governing equation, let me write it here itself. So, minus m1 omega square capital X1, right, cos omega t, because when you take the second derivative of this, what will happen? X1 double dot of t would be capital X minus omega square cos omega t. Similarly for X2. So, the first equation here would turn out to be this K1 plus K2, this one will be X1 and then it will still be multiplied by cos omega t, which I am going to take out as a constant term here, multiplying term, same term appears in all the terms there, which actually means what? I can write this as x2 over x1 equals k1 plus k2 minus m1 omega square. This is the multiplying factor to x1 and then this is going to be k2. Or I can write vice versa, the ratio of the two amplitudes may be x1 upon x2 as minus k2 over k1 plus k2 minus m1 omega square. Okay, that is what I possibly have here as one equation that I get by solving the first equation by substituting the assumed solution, which is actually called as a principal motion, wherein both masses move with the same period of time. And you will get by substituting into this second equation, you would get this as what? So, minus m2 omega square x2 plus k2 plus k3 into x2 minus k2 into x1 multiplied by the entire thing multiplied by cos omega t, of course, equal to 0. So, when I reorganize this, x1 over x2 will turn out to be what? M2 omega square, let me write first the stiffness related term. So, I have K2 plus K3, right, minus M2 omega square, they are all connected with x2 and x1 will be K2. Done. What does this mean? If one ratio is equal to this and the same ratio equal to this, these two ratios can be equated. So, now is the job of further simplifying this, and by using equation 1 and equation 2, that would give you what? K2 square equal to K1 plus K2 minus M1 omega square multiplied by K2 plus K3 minus M2 omega square. all right. You solve this, what you expect? A quadratic in omega square, right. This is what you will get from this. It is a simple straightforward mathematical process of getting a the equation, that is your frequency equation. Okay. Let me clear this off now. So, we did this, got these equations, we said that okay, this is the normal motion or a principal motion of the system, and then when we substitute we got the governing equation simplified, we got these governing equations with the substitution turning out to be or giving the ratios between the two amplitudes of the two masses x1 and x2, that is what we wrote. And by solving this you get of course here the instead of omega it is p, but then that refers to the same frequency of motion p, and you basically get this equation by solving the last equation on the previous slide. You will get a quadratic in p square, and that if you solve is given as the frequency expression. That means, if you substitute for k1, k2, m1, m2, you get the two natural frequencies of the vibratory system. So, of course, P1 is going to be P1 square is going to be the first squared natural frequency, P2 square is going to be the second squared natural frequency. You remember that we got by solving the single degree of freedom system equation, omega n square was k over m, right. So, this is the only equation the only natural frequency that we got for a single degree of freedom system. In this case, the system is having two masses, and then the frequency equation is not as simple as you got it for the first single degree of freedom system. The equation here is little more involved, and the expression for natural frequency looks like this. You substitute each parameter and then you get a numeric value of the natural frequency by using one of the signs. If you use the negative sign here, you will get the first natural frequency. If you get the positive sign here, you will get the second natural frequency. Okay? You will get two natural frequencies from this equation. Is that clear? Now, these two are the natural frequencies. What does that mean? That the system will vibrate at one of these two natural frequencies, but we started this whole process with the assumption that the motion given, the motion given was x1 and x2, and we forcibly presume that both of these two masses will move with the same time period. Now, the system does really have a possibility of vibrating at one of these two natural frequencies, provided the motion that we have assumed has to be with the amplitudes x1 and x2 which maintains this ratio. Okay, which maintains this ratio, which means that as long as the motion of the two masses have the amplitude ratios given by this particular right hand side value, the two masses will continue to vibrate with natural frequency either P1 or P2. Of course, if you substitute for P1 in this equation, you will get one number, okay, and if you substitute for P by P2, you will get another number. Okay. So, if you maintain the number obtained by substituting P1, this amplitude ratio is maintained based on this value obtained by substituting for P1. That ratio, if you maintain, the system will execute harmonic motion at a frequency of P1. If you maintain the amplitude ratio which is given by a value on the right hand side by substituting P for P2, you will get the motion executed with the frequency of P2. Please make a note, natural frequency P2 or natural frequency P1 means that both of these masses will harmonically move and then they will move with the same time period. They will reach their mean 0 position at the same time, then they will reach their maximum amplitude at the same time. If they do not follow the process here, if they do not follow this amplitude ratio, this mass would be moving somewhere here, whereas this mass would reach the mean position. And if you mix or add these two motions, you will get a periodic motion, not a harmonic motion. Okay. When I say they will reach their peak value, does not mean that they will reach their peak positive value. They may have this may reach peak value negative and this will reach their peak value positive, but then they will reach the peak value simultaneously at the same time. That is what the basic thing is, relating the physical motion and relating it with the mathematical expression here. So, we will take a small example, having obtained the expressions for this amplitude ratio and the expression here. We would take a small simplified example. This is more generic. We will take a simplified example which will further clarify what this motion is, what we are talking about. Now, you would wonder that when I discussed and started giving you an idea about this principal motion, I said you start moving them together, right. So, this amplitude ratio is to be honored at all times. So, it could be the starting amplitude ratio. That means, I can move this with some amplitude maybe 1 unit, and I can move this with the same amplitude 1 unit and then release them. What will happen? It will execute this kind of a motion. This will also execute the same kind of motion with the same time period. Because this ratio has nothing to do with at what time of the motion, if you honor it at time t is equal to 0, it gets honored at all times. Okay. So, all of these will be discussed in the context of a simpler example that follows now. Okay, this is what we discussed today. We got introduced to a 2 degree of freedom system, and we derived the governing equation of motion for a simple 2 degree of freedom system, and understood the concept of a principal motion. These are a few recall questions based on today's lecture. And these are the answers.